Bismillah ar-Rahman ar-Rahim. Let's continue our wave propagation. So we have just learned Joukowski, we have learned maximum pressure, we have learned the pressure history. So we need to get a little bit in detail of our wave propagation, which is a very nice picture. You can relax and sit and see things going in front of you. Simplified model. Let's start with a very simple model. Simple model means a reservoir, pipeline, valve with length L, reservoir edge, no friction, hydraulic gauge line horizontal, time 0, nothing happened before, it was steady state before, we are gonna instantaneously close the valve. This is called a simplified model, instantaneous valve closure, sudden, no friction. In the same time, two things has to be taken care of. One, elastic pipe wall. Two, compressible liquid. Elastic means it can stretch, it can elongate in the diameter, it can stretch in the length, delta L or delta D diameter, and the liquid is compressible. The liquid can compress, the density will change with time. This is called simple model. So somebody will tell you this is not a simple, but let's consider this as a simple model to see what will happen. Simplicity here because the friction is 0 here. This is where we can see everything clearly. The pressure rise due to the water hammer depends on wave speed. Yes, it's A or C. The velocity of the flow in the pipe, if it is velocity V. The length of the pipe, which is L. Time taken to close the valve. The system response. How much time it will take you to close the valve. If someone close the valve in a full day, nothing will happen. I mean, things will be nice and simple. If you close it in a 0 time, 0 second, it will be a disaster. So it's too extreme here. Sudden valve closure, consider a pipe L connected at one end reservoir containing height H from the center line of the pipe. Consider the ideal flow F0 at the other end of the pipe. A valve to regulate the flow of water is provided. Pipe flow velocity is V. This is the situation which we have. What will happen actually? What will happen here during our valve closure? Things will happen. We know that the pipe was flowing with velocity V. We know that there is a kinetic energy there related to the velocity which will happen. And also we know that as soon as we close the valve, there is things will transfer to a potential energy, and it will be a big force will be impacted the valve. Our needed to be active because the valve, there is a big force will affect the valve due to the increase of the pressure. So again, the kinetic energy of the water moving through the pipe is converted to a potential energy stored in the water. And the wall itself of the pipe through elastic and through the wall and of the pipe through the elastic deformation of both water and the pipe. You know, elastic deformation of water means compressibility. Elastic deformation of the pipe means things which come longer diameter, larger diameter, or stretching on the length. Water is compressed. We understand that. And also pipe material is stretched. Pipe material, it will be elongated a little bit on the transverse direction and along the diameter direction, axial direction and the diameter direction. The following figure illustrates the formation and transition of the pressure wave due to the sudden valve closure. Situation like this, there is a reservoir, hydraulic gradient horizontal, instantaneous closure, elastic pipe wall, compressible liquid. Two things here, the pipe elastic and the liquid compressible. And the velocity still working with positive velocity with the same V value. This is at time zero, everything is open and the flow is going normally. Suddenly you close it. We close it at time zero. In the same time we close, things are happen like that. Two things happen. The particles of water attached to the valve will have the same velocity of that part, which is zero velocity. So the blue color here represent velocity zero. In the same time, there is an enlargement on the pipe diameter, which I showed here, exaggerated of course, with that increase in the diameter this way. So two things happen, velocity zero, enlarged diameter a little bit. And then it will propagate. It will propagate with the speed A. So this change will happen here due to the valve closure, which is accompanied by a V equals zero and increase on or stretching on the pipe diameter. At the same time, there is an increase on the pressure happen due to that change from kinetic energy to the potential energy. Assume that ideal flow, no friction, and the valve was initially open. You close it. When the valve is suddenly closed, large force is needed to decelerate the fluid. The fluid we need to stop the fluid. So it needs a large force to decelerate the fluid, and this force appears in the system as a pressure. So the things will try to stop that fluid with the pressure. Sudden increase in the pressure occur at the valve location. As we said, there is a sudden increase here. And this accompanied by pipe stretching. We call it pipe bulk. Bulk means increase in the diameter. An increase in fluid density. At the same time, you have compressibility of the liquid. The blue color show three things in fact. One, the velocity is zero at that blue color part. Two, there is a stretching on the pipe diameter, there is a pipe bulk. Three, there is a change on the fluid, increase in the fluid density due to the compressibility. And another things happen. There is an extra volume of fluid is stored in that pipeline. Do you know that sense? Due to that increase in the pipe diameter, due to that a bulk happened there, there is an extra volume of liquid stored on that part. This will propagate with time. Time L over A, this is the time required from this wave front to go quickly to the reservoir. So at L over A, this wave front, the red wave front here, it will reach the reservoir. At the same time, at the same exact location of the wave front, what will happen? There is a stretch in the pipeline, there is a compressibility, increase in the density, and also the velocity is zero. Do you see that? All this together on that diagram, you can see it. You can see increase of the pressure due to the closure that happened, that change in the kinetic energy to the potential energy. In fact, this is the momentum equation change. This is a V equals zero in the blue color part of the pipeline. There is an increase stretch, the bulk happened, which stored some liquid there. At the same time, the velocity equal to zero. This is time L over A. This pressure wave propagate upstream at the speed of sound, speed of A in the medium. Okay, so it will go there. Remember, this part of the section or this section of the pipe doesn't feel anything. This section of the pipe still passing with the same normal velocity. This part has the same normal velocity, except this area has a velocity zero. So as long as the wave front will move, this will be increased, and this is still the same velocity in the same direction. So at L over A, what will happen? The picture will show the full pipe length will have zero velocity. The full pipe length will be stretched in diameter. The full pipe length has stored some liquid fluid. Full pipe length has velocity zero here. So increase in the pressure, zero velocity, compressibility of liquid. What will happen next? The next part here, due to the momentum equation at that part, you will see that relief backflow to the tank goes part of the water which is stored there, that it will go back again in the other inverse direction, means that velocity will take minus sign. The velocity of the pipeline, not the wave, the velocity of the pipeline will have a minus velocity. And this return back to the normal diameter here. And the wave speed will go to the downstream with the same velocity A. It is not changing. The wave speed will not change back and forth. It will be the same. So this is at X distance up from the pipe, from the reservoir. Everything will go up to reach up until we reach the valve location. When we reach the valve location, all the pipe will experience a negative velocity. All the pipe will experience exact same pressure as initial H node. Okay? And there is no stretching, there is no compressibility, everything at 2L/A exactly returned back, except the only difference here is that the velocity on the inverse side, negative side. Again, what will happen next? What will happen next? A negative wave will come from the valve to have, instead of stretching the pipe, it will be reducing the pipe. Due to that negative things, it will reduce the pipe diameter. Velocity is zero, and the reduction in the diameter and the relief of the fluid to the tank back one more time again, and we'll see that in the 3L/A. At 3L/A, everything will experience a minus delta H, a minus Joukowski pressure, minus A delta V/J. So the static level is the same. It will not change. The only thing you're going to add one time delta H, or you subtract delta H from it. Again, the last cycle here, the relief from the tank, velocity will be positive direction, diameter will return back again, velocity will be positive, and then the wave front will move until it reaches the valve and return at 4L/A. Everything will be the same at the beginning. Everything will return to its initial condition. The pressure is horizontal without any reduction. The velocity in the positive direction. The diameter is exactly the same. The velocity is positive. There is no compressibility, nothing else. So at 4L/A, we return. The question at the end, please. Okay. We return back. We'll return back everything to normal at 4L/A. So what we will see here, what we will see at the valve, we'll see that shape. We'll see the stepwise diagram. At 2L/A, you will have a positive pressure, and the other 2L/A, you will have a negative pressure. Again, it will repeat it forever. Why it's forever? Why it is forever? Because this is the frictionless. Okay, again, this is the velocity at the valve. It's a zero at the valve, except for the small amount of time at 2L/A or at 4L/A, you would have that positive or negative pressure. You can see it in the previous slide, why it is like that. At the reservoir, normally at the reservoir, pressure are always the same as the head of the valve, except at L/A, when the wave reach the reservoir, has that high things, and when at the 3L/A it has a negative, and then it return back again at 2L/A, at 4L/A to the original head again. Okay, this is the velocity at the reservoir. So, in another word, I can draw the pressure history at the reservoir, or at the valve, or at any section I need to calculate. At section I, you can draw things exactly similar. Time history for the pressure wave. Water hammer, the time history of the pressure wave for a specific point on the pipeline. I can ask you to draw the pressure history at any point on the pipeline, similar to what we have done on this PowerPoint presentation. And this will be first exercise to you during the tutorial. A graph that simply shows the relation between the pressure increase delta P and the time during the propagation of the water hammock pressure waves. This is called the pressure history. Another presentation, if you don't understand the first one, I'm gonna go with you quickly, step by step. Remember, this distance is L over 2A. Remember, before we have the full distance is L over A. L over A means from the valve to the reservoir, I'm going to take L over A time. So in another word, to go L over 2A and then another L over 2A, so as if I'm going the trip here in two parts. Let's see how we can do that. Pressure variation at the valve. I am drawing the pressure history at the valve. So if I start, look for both this part and this part. This is exactly in every step, I'm going to increase the pressure. It will go to reach L over 2A. It will be up to the half here. It will be like this. Another L2 over 2A. It will give you 2L over 2A. It's L over A. This is L over A. If I continue up to here, it will give you 3L over A, 2A. Up to here, it will be the same 2L over A. It's 4L over 2A, 2L over A. It's like this. And then I can go for the third cycle. Up to here. It will give you here, like that. Another half cycle. It will be like that. This is the third one. Let's start the fourth one. This is half part, and this is the full. When we reach the last one, it will return back to that point here. Okay, so at 8L over 2A means 4L over A. Again, it will give you the step cycle. So this is a stepwise diagram, which will give you the increase in the pressure, the decrease in the pressure. This is the distance from here to here is 2L over A. The distance from, or the time from here to there is 2L over A. This is the H, which represent the static head. And the increase here represent the delta H positive, and the decrease here represent the delta H negative. Okay, so when you calculate the total pressure, the maximum total pressure, somebody will tell me what's the maximum pressure here. The maximum pressure I will calculate, it will be this one plus this one. So the maximum pressure experienced on this pipeline, it will be H plus delta H. What will be the minimum? The minimum pressure, it will be the static minus the delta H. It will be this one only. So two things has to be calculated here. The maximum pressure, the minimum pressure. So the pressure history, the value of the pressure history, it will give you the full diagram of the time history of that experience at the valve. It will give you the maximum and the minimum that will happen at the valve. Okay? Pressure variation at the reservoir, simply, if I'm standing at the reservoir and I'm trying to draw the pressure, it will be, assume that you are standing here. So everything will be remain constant here until you reach 1L over A. You will have an increase, but return back quickly to be the same here again, which is at the valve, at the reservoir. Still constant pressure at the reservoir, constant pressure until you reach here exactly at 6L over 2A. It means 3L over 2A. You will have a negative pressure quickly, and then it will return back pressure here equal to the same reservoir head until it reach the 4L over A. Okay? So this is the shape which you can see. This is the shape which you're going to draw for me if I ask you to give the pressure variation at the valve, or the pressure variation at the reservoir, or the pressure variation at any place. As we go near the source of disturbance, you can see that, you can get that conclusion. Whenever you go, if you draw the pressure history at the valve, you will have either above or below the normal pressure. If you go, on the contrary, if you go to near to the reservoir, you will have a steady pressure, except in a short period of time on the 2L over A or L over A or 3L over A. This is a summary of everything we have talked about during our lecture, which can show to you the 1 at the sudden valve closure, 2 at L over A, 3 at this part, 4 at 2L over A, and then like this, and then 3L over A, and then 7, and then 8, return back again. This is what you have to draw at the end. You have to get the pressure variation over time, pressure variation, valve velocity, head, and friction losses neglected. If you are looking for the damping effect or the amplitude, damping of amplitude through friction, if you can see that diagram, this is the pressure wave, pressure history, pressure versus time at the valve. You can notice the decrease on the pressure head. You can notice the decrease in the pressure head. And this is what will happen if the valve closing time is smaller than the run time. Remember, we are talking about a sudden valve closure. You remember on the last lecture, when we say a sudden valve closure, it means you close it at 0 time, or you close it with a time less than or equal to L over A. You will have the Joukowsky pressure. Joukowsky pressure, you will experience the Joukowsky pressure at the first cycle. The first cycle, you will have the maximum pressure. But the second cycle, it will be less due to the effect of friction. The third one, it will be more lesser, and then it will damp away until it will reach steady state, as we have said before. In real practice, friction effects are considered, and hence the damping effect occurs and the pressure wave dies out. It's called energy dissipation. This is what's the purpose of Darcy equation, which is Darcy friction factor F with Darcy HF equation, which is FLV squared over 2GD. So it's when we simulate the friction losses inside our momentum equation, it will give you that effect of reduction. We'll learn this later in our next lectures. This is the way which you can show if you add the friction factor. Remember, the friction factor has a research topic. Research topic means you can use friction factor, constant friction factor, you can use unsteady friction factor, you can use frequency dependent friction factor. This is a topic that's beyond the limit of this course, but you can see that the actual shape of the wave, which is the green one, it will be less than if you use the steady state friction factor. If I use F constant, you will have the blue or the purple one, and then the green one if you have a frequency dependent friction. This is beyond the limit of our course. Sudden valve closure, another factor we need to look at. In the long pipeline, in a very long pipeline, in the order of 100 kilometers, you tell me whatever you're going to normally work, you're going to work with in the order of 10 kilometers, pipelines of 1 kilometer, 2 kilometers, 3 kilometers. We call this short pipe. A very short pipe, it's less than 1 kilometer things. So it's a long pipeline in the order of several hundred kilometers. There is a chapter for this one. Again, I'm gonna put this slide for the sake of completeness to that course. We have things called potential surge. The potential surge is the one which we have learned, which is the Joukowsky pressure. So the potential surge here, this is the pipeline. This is a 125 miles, okay? It's a very long pipeline. This is the valve. And this is a steady state hydraulic grade line. This is the potential surge, which is the Joukowski pressure minus A delta B على G. And what about this? What about this increase here? We call this as a line packing. We call this attenuation here. The line packing, I can imitate this for you, like, for example, just for the sake of simplicity to that topic, imagine that you have an open channel, an inclined open channel, and you have a gate at the downstream. You will see the water level rise in front of the gate. It will rise, okay? This is called line packing here. This is what we imitate that by those number of 1 minute, 2 minutes, 3 minutes, 4 minutes, number of minutes after valve closure. The pressure will rise above the potential surge. This is another things you're going to learn in our exercise. I'm going to give you a very simple exercise to show that for you. So line packing, wave attenuation, and as I said to you, if you are interested, you can go to chapter 7 in our book. But this is, we are going to take this as an exercise in our project. Again, for all of you, for short pipeline, this is what you're going to see. A valve, an increase of the pressure, the wave will go back and forth this way. If I have a valve in the middle, positive wave will go upstream, a negative wave will go downstream, and this is the way of doing that. The one before is very long pipe, very, very long pipe. You will see the line packing. You're not going to see the line packing in a short pipeline, all right? Hammer project. So what's the Hammer project? I'm going to give you a brief on the Hammer project. Allow me to stop recording here. Oh, no, let me keep the recording. The main objective of this project is to get familiar with Bentley Hammer interface. The session will include how to model the simple reservoir pipe valve system. By the end of this session, you're going to you'll set the Hammer program, you will set the project, you know how to deal with the scenario, alternative model different, you will model different type of control valve, you will prepare output results, figure, graph, animation, and text report. So you're going to submit to me a text report, including some clips from picture from your output to show to me that you have done the exercise properly. And then the project is like that. It's a tank starting from 200 meter in the center line elevation to 300 meter top of the reservoir. It's 100-meter reservoir. And the diameter is 300 millimeters. It's horizontal pipe. It's a ductile iron, E thickness 3 millimeter, PVC thickness 16 millimeter. It's a valve at the downstream. So what's a system we're going to study? We're going to study a sudden closure, which is the first part here. We'll have different pipe material, ductile, iron, with short pipe, long pipe, PVC, short pipe, frictionless short pipe. So this is what the material we're going to study. We'll have a pipe length 1,000, 1 kilometer, 10 kilometers. We're going to see the difference here. On the other part of the project, we'll have a linear closer in 60 seconds. We have a gate valve, butterfly valve, and a ductile iron, the same ductile iron pipe, which is a 1,000. We're going to use 2 different valves. In a simple categorization, this is not a group. Everyone will work alone here. It's not a group for student. The group of results here, it will be one group for the sudden closure and the other group for gradual closure in a 60 second. The first group here, it will be a ductile iron 1,000, 10,000, PVC 1,000, and the frictionless pipe, 0 friction. And the other group will have a gradual valve closure in 60 seconds, use 2 valves, 1 gate valve, and the other one is butterfly valve. Things which you're going to see in your analysis, it's like this. This is a valve closure, a sudden valve closure, like this. This is a back and forth. Remember here, I am opening the negative parts, so you can see all things, positive and negative. This is the way you can see the positive and negative. This will go in several seconds. And remember, this is a 1,000 meter pipe. For the second one, it's a 10,000 meter pipe. I will have friction losses like that. You will see the line packing a little bit, and this will be the maximum pressure envelope. You will see that how it will proceed back and forth.